This week we're going to look at gravity, and gravity was one of Newton's contributions, one of his additional contributions to physics, was trying to explain why objects tend to fall when they're near the Earth's surface. This was something that confused Newton because, according to Newton's three laws, forces have to act on things to get them to accelerate, and that's easy to see if you've got two things hitting each other, or if you're pulling on something. That makes sense. But there was kind of this magical thing that if I let something go near the Earth, it just falls to the surface. And so he posited this idea of gravity, which was a force that acted at a distance, that if something had mass, it tended to draw other things with mass to it. And this turned out to have some pretty good advantages because it explained not only why things fell on the Earth, but it also explained why the moon stayed in orbit around the Earth and why the planets orbited the sun and that sort of thing. So it's a pretty powerful description. Turns out it's going to take Einstein to figure out what gravity really is, which is a bending of space-time that changes the trajectory of things in space. But we're going to talk about that a little bit in this chapter. But for now, I just want to talk about Newton's law of gravity. So if you've got two objects, and they can be any two objects, we'll call this M1 and M2, and they happen to be a certain distance away from each other, they're going to experience equal and opposite forces pulling them together. And that's the force that we call gravity. And if we know the distance between them, you can write down that force as being proportional to the masses, the product of the masses, and the distance between them. And this constant g is a constant of proportionality, which has to be measured. It doesn't. We can't derive it. It's just something that is a feature of our universe. And you can do this by a number of different ways, basically bringing two masses close to each other and measuring the force between them. But this value of g is 6.67 times 10 to the minus 11 in MKS units. And you put in the units that you need there to make this come out to newtons. So that's the gravitational force that you can calculate. And because if you have, the reason this is so cool is that it explains why objects fall to the Earth, right? But it also explains why they orbit, because if you give something velocity in this direction, it's going to fall to the Earth, but while it falls to the Earth, it's also moving in this direction. So it begins to take on a trajectory that looks like this. And if you're going fast enough, you never intersect the surface of the Earth. Now, if you're going really slow, eventually you'll just fall in and hit the surface of the Earth. But if you're going fast enough, you'll stay in orbit around the object. And because of Newton's first law, an object in motion tends to stay in motion unless acted on by a force. Its position will change in the x direction. Its velocity will be going in the x direction, but its position and velocity will change in the y direction towards the central mass. And so you'll end up getting this thing track in an orbit around, and it'll just go around perpetually unless energy dissipates and causes it to fall in. But there's nothing to run into out in space, so the moon just orbits the Earth like that. Okay, so that's telling us how this results in orbits. But how is that connected to what's happening on the Earth? Well, we've already talked about this idea of the acceleration due to gravity. This is a measured property of the Earth, 9.8 meters per second squared. But we can set those two things equal to each other. We can set mg is equal to gm. We'll call this one m1, and we'll call this one m2. So we have g m1 times big G m1 m2 over r squared. And because the inertial mass, which is this mass that's experiencing the acceleration, is equivalent to the gravitational mass of the object, we can cancel those. And we get that the acceleration due to gravity is proportional to the distance you are from the object and the mass of the object. And this is kind of cool because it gives us the ability to measure the mass of the Earth by measuring the acceleration due to gravity. But it also lets the gravitational acceleration vary as a function of distance from the center of the object. Okay, so there's our connection between the falling of objects and the orbit of objects that Newton's law of gravity did for us. We can also calculate potential energy. The potential energy for an object, we've talked already. If you have a flat surface and you're very close to the surface, that we can write down the potential energy as just mgh, like that. But what happens as you start to move further away? As you start to move further and further away, that force of gravity that is giving you that potential energy is going to change, right? And ultimately get out to a certain distance, and you're going to have a maximum potential energy. So if I lift this thing up to infinity, it's going to have the most potential energy it can to fall down onto this surface. So we do a convention here where in the past we've called this the 0-point potential energy, right? Because it was convenient for us to be able to calculate h as a positive number. Here what we're going to do is we're going to call zero potential energy here. So we're going to say at r equals infinity, we're going to have the potential energy is equal to 0. But remember, that's the maximum potential energy. So that means that it has to get smaller and smaller and smaller. So when we get down here, the potential energy is going to be negative. And when we write that down, we can imagine, putting in our gravitational force, m. We're going to put in our g m2 over r. Our distance away is going to be r, like that. Those are going to cancel. And we put in a negative sign to make sure that this is smaller than this over here. And we get our acceleration, or our potential energy due to gravity, as minus g m1 m2 over r. And again, this negative sign just goes in there so that when I put in r at infinity, this is 0, but that has to be the maximum potential energy. Now what's cool about this is that means we can calculate some interesting things about objects that are in orbit. For example, we can calculate something called the escape velocity. The escape velocity tells us how fast we need to go to escape the potential energy of the Earth. So if we think about, having an object here on the surface of the Earth, and we launch a rocket straight up, and we want that object to get to infinity, the question is how fast would it need to be going to do that? Because as it accelerates away, as it speeds away, it's going to lose velocity because it's climbing out of this potential well. So we go ahead and write down our initial kinetic energy. The initial kinetic energy is just 1/2 mv squared, and we're going to treat the initial potential energy as just equal to minus g m1 m2 over r. But in this case, this is going to be the radius of the Earth, right? And then our final potential energy is going to be minus g m1 m2 over r. But this r is going to go to infinity, so that's going to be equal to 0. So that means I'm going to get 1/2 mv squared minus g m1 m2 over r Earth is equal to 0. Those m's are the same, so they're going to cancel, and I'm going to wind up with the escape velocity is equal to the square root of g m2 over r Earth. And that is the mass of the Earth, that's the radius of the Earth. If I put those numbers in, I get 11,200 meters per second. So you can calculate from the acceleration due to gravity, or the potential energy due to gravity, you can calculate how much energy you would need to escape. You can also calculate from the centripetal acceleration the energy you need to stay in orbit. So if you have a planet like this and you want to orbit it, you're going to be experiencing an acceleration that is equivalent to our acceleration due to gravity. And the question is, what velocity do you need to be going in order to stay in that orbit? But this is centripetal acceleration, so I can just set this to v squared over r, right? And so my r's are going to cancel there, and I'm going to get v is equal to the square root of gm2 over r. And I just realized over here I forgot my factor of 2. Haha, there we go, factor of 2. Okay, so this is our orbital speed. And that depends on distance. The further away you are, the slower you can be going and still stay in orbit. Very close to the surface of the Earth, this is something like 8,000 meters per second.